Hello. So in this video, we're going to look at Haberman's section 10.3, which introduces and discusses the Fourier transform, which is kind of the main tool that we'll be using for the rest of this chapter and course, really. Cool. So what are we going to talk about? Well, first, we're going to try to motivate kind of this Fourier transform, which we're defining for kind of functions on an infinite interval, right? The kind of questions we're looking at now are solving the heat and kind of other PDEs on an infinite interval. So what we're going to do is we're going to see how we can kind of get this Fourier transform from kind of a finite interval, kind of in that, what that motivation is. We'll introduce the Fourier transform, introduce some very basic properties, and then we'll compute the Fourier transform of kind of a Gaussian, which usually for a Gaussian we'll write, so what is a Gaussian? A Gaussian is some function of the form e to the minus alpha x squared, and then maybe some constant in front. And so it turns out that kind of these Gaussians play a very important role in working with the Fourier transform, especially in trying to kind of construct and compute solutions to certain PDEs. But yeah, let's get started. So kind of what is the motivation for all of this? Well, if we take kind of a bounded interval, negative L to L, right, which we can draw as this. So that's 0 minus L to L. And we take any function, say f of x defined on that interval. So it's going to be f of x. We can write it, we can express this function in this form, right? Where we have this infinite sum of some constants c sub n times these complex exponentials e to the I n pi over Lx, where, right, what are these constants c sub n? Well, integrate the function that we care about against e to the minus I n pi over L x, integrate that between negative L and L, normalized by 1 over 2L, and that's what we get, right? And so one question is, well, where do these coefficients come from? What we can do is we can say, well, if we take f of x is equal to the sum, say n equals minus infinity up to infinity, of some mystery coefficients c sub n times e to the I n pi over Lx. What we can do is multiply on both sides by e to the minus I m pi over Lx, e to the minus I m pi over Lx. And then we'll integrate kind of over the entire interval. So integrate from negative L to L dx. So the only integrals here that are non-zero are when n is equal to m, giving you kind of the integral of e to the 0, which is 1. And so then that's where we pick up a 2L from. This isolates kind of the coefficient, or one of these coefficients. And then otherwise, this is the integral that appears right there. Okay, so we can do the same trick we did with Fourier series, right? Multiply by cosine or sine, integrate. But this is kind of this complex representation. Okay, so what we can do is say, okay, sure, we have, this piece right here. And so what do we get if we actually plug this in into that series representation? Well, we're going to get this representation, okay? And so keep in mind here, right, what we're doing is we're saying this integral in here, right? So if we go back here, so c sub n, right, we're integrating out the entire function, right? F of x, x is up there with respect to x. So this whole thing is going to be a constant, but, right, if we change this to any other dummy variable, all is well, okay? So that's what we're doing here. We're just changing the variable that we're integrating against or with respect to in here. But otherwise, this is more or less the same thing that we had in the last slide. Okay. And so what we'd like to do is try to figure out how we can connect this representation to that for an infinite interval. Okay. And so what we're going to end up doing is take something like a limit as L goes to infinity. Okay. And so as written in this way, if we just let L go to infinity, it's maybe not super clear what we're going to end up with, but if we make some kind of appropriate substitutions and kind of play around with these pieces, then the right sort of infinite interval analog, that'll pop right out. Okay. So let's see what happens. Cool. So what we're going to do is, right, kind of in the last chapter, we were looking at these quantities omega, right? And omega squared, these were the eigenvalues for the problem. So right here, so omega squared equals lambda are eigenvals for the ODE d squared phi dx squared is equal to minus lambda phi, where phi is going to be finite, or phi is going to be bounded as you head off to positive or minus infinity, right? And any omega worked. So in this case, though, for the finite interval, the omegas that we're allowed to work with are going to be discrete, right, of the form n pi over L. And so, of course, omega is still going to go off to infinity, right? L is fixed and increases, but they're discrete. So what you can do is, well, kind of rewrite this in this form, 2 pi times n over 2L, right? And so if you go through, right, choose cancel, we're left with pi times n over L. So, you know, this equality holds. But yeah, so what we're going to do is we're going to work with this representation. And so, sure, what is the gap between successive wave numbers, right? So this is going to be kind of a wave number, say for n+1 times pi over L. The distance between that wave number and the previous one. So that's going to be n pi or n+1 pi over L minus n pi over L. Okay. Do the arithmetic, we end up with pi over L. And so one thing to notice then is that, let's see. So from this, we get that what 1 over L is equal to delta omega over pi. So 1 over 2L, right, which is a term that we see down here. 1 over 2L is going to be, let me rewrite this. Delta omega over 2 pi. Okay. So this is just re-expressing this quantity 1 over 2L that appears right there in terms of these wave numbers or frequencies. Okay. Well, what do we get, right? So this is the identity that we had in the last slide. Okay. This is a Fourier kind of representation formula, complex exponentials. And so if we plug in this expression for 1 over 2L, we end up with this thing right here, right? Where, I guess if I want to keep the brackets, so this is going to be that, and then that-ish. And so keep in mind here that, right, here we're summing over n, okay? If we look in here, well, there's no real n, okay? But how we're kind of bookkeeping things, omega depends on n, right? So as we sum from n equals minus infinity up to infinity, we're summing over all possible omega. Okay. Great. So it may not look like we have much, but right, what we did is we plugged in, whenever we had this n pi over L, right, we plugged in for omega. And so now we have a sum times a tiny increment in omega times, right, some function involving omega. Okay? And so now this might start to kind of remind you of Riemann sums. Okay, and so especially as, right, L goes to infinity, right, if we take this interval and make it larger and larger, delta omega is going to shrink to 0. So this gap, kind of this increment, is going to get smaller and smaller, and we'd expect that we pick up some sort of Riemann sum, which converges to some sort of integral in omega. So let's see what that looks like. Right, so this all is getting at then the Fourier transform. So what's going to happen is as we take the limit, kind of the integral that we pick up, kind of in here, the piece that pops out is what we'll call this Fourier transform, and this summation over here, that'll turn into an integral. Which will be kind of where this superposition principle kind of comes into play. Okay. Right, so what happens, let me add back in kind of the parentheses here. Right, so what happens is L goes to infinity. Right, so if we have some interval here from negative L to L, right? As L goes to infinity, these boundary points are just going to keep going off to infinity. So our finite interval, right, is going to tend towards this infinite interval. And like kind of what we noticed before, right, this increment delta omega, that's going to tend to 0. Okay, so what's going to happen is, well, we have this, right, representation from before, where we're using kind of this delta omega over 2 pi instead of 1 over 2L. So what we're going to do is we're going to take this 1 over 2 pi, move it out front, that's that. And we're going to take this delta omega, which again depends on n, and we're going to take this delta omega all the way over here. Okay. So then we end up with this expression right here. Right? Cool. So now, if we take the limit, say, as L goes to infinity, what's going to happen is, right, these endpoints, this is going to go to infinity, this is going to go to minus infinity, which is what we have here. And here we're taking a summation of some function of omega with respect to this tiny increment. And so as this increment goes to 0 and we sum up all these pieces, right, in the limit, we're going to pick up this integral with respect to omega. Okay, and so a slight correction here. So if we go back to this last slide, yeah, so here we have this e to the I n pi over Lx, plug in omega for n pi over L. What we should end up with over here is e to the I omega x. And that typo is carried over here. So this should be, so I'll remove these. Last one's fine. This should be e to the I omega x, e to the I omega x. Okay. But the point is that if we kind of keep track of this 1 over 2L term in the right way, then we can recover kind of this sort of integral representation, right, for this function f. Okay. And so kind of for our purposes, right, I mean, right, two things to note. One is we have this superposition principle, right? We're summing up over these basis functions, e to the I omega x. And then the other piece to keep in mind is we have this interesting coefficient in here, right? This thing is a function of omega. And what we're doing is we're integrating out f of z, right, the function that we care about, multiplied by this function e to the minus I omega z, and then integrating out in z. Right, which is very similar to what we had before with the c sub n, right? It's just now we're integrating over the entire domain. And in some sense, the constant that we get out front, instead of a 1 over 2L, in some sense, the constant is now 1 over 2 pi. But anyways, okay. So that's that constant. Cool. So what we're going to do is we're going to define the Fourier transform as that inner integral. And so as you can see here, we're actually tacking on this 1 over 2 pi with the integral, okay? But this thing right here is exactly what we had, right? This 1 over 2 pi times this thing in here. Okay. So this is what we're defining to be the Fourier transform of a function f, defined on the entire real line. Okay. And so one comment to make, there's a lot of different notation out there. Some that we'll see kind of in this course are, so this capital F of omega, where it's understood that, right, if the function that you care about is a lowercase, say f, then the Fourier transform is going to be capital F. Notation that's a little more popular kind of in the literature and actual research is this f hat, right? So just add a little hat above your function. If you really want to focus on kind of the fact that you're applying some sort of operation to a function, then sometimes people write it in this way, where you have a calligraphic f, and then you're applying it to a function f. So then this whole thing right here is going to be your Fourier transform, okay? These three things are just alternate notation for the same object. What is that object? That's this integral. And so keep in mind that, right, with this integral, right, we're integrating out in x, okay? So we have a function of x, we're integrating out x. Otherwise, we have an e to the minus I omega x. I is a constant, x we're integrating out. So the only free thing in this whole expression is this omega. So this whole thing right here is in fact a function of omega. It depends on omega, right? And so that's why we're saying, right, the Fourier transform in all of these cases is a function of omega. Okay. Okay. And so one thing to note, right, in this last slide, what we did is we said, well, here's our function, right? And then kind of suppose it's defined, you know, kind of successively on these larger and larger intervals, right? What we're going to end up with is this kind of integral representation. I can write, so this is equal to f of x. That's what we'd like to say. And this is in fact the identity. And so back here, we can say, well, sure, we had this identity over here, right? And so what we can do is, right, move this 1 over 2 pi in, plug in for this whole thing right there. So another way to write this identity is that, well, your function f of x, this is the integral of your Fourier coefficient times the corresponding kind of basis function, and then you're integrating out kind of your frequency or your wave number, right? You're summing all of those up, and that's your function. Okay? And so if instead of using a hat, you want to use capital, it's just different notation. Okay? And so one caveat that I want to mention is technically, right, if we go back to this representation, technically this equality holds wherever f is continuous. Right, so so this holds for f continuous, right? For f discontinuous, then this whole thing, this was the average of the left and the right limits. Okay. And so, of course, when the function is continuous, the average of the left and the right limits is just the value of the function itself. When it's discontinuous, you may not get the value of the function. Okay. So that's something that kind of in sweeping under the rug and in practice won't really be an issue. When it is an issue, kind of we'll explicitly mention and kind of be careful of that. But anyways. Yeah, so the running assumption for all of this will be that, right, the function f that we're taking this Fourier transform of is going to be continuous. Okay. Cool. So yeah, so related to the Fourier transform, right, if we plug in a function, integrate against these functions over all x, we're going to get a function of omega. Oh, and my slides are frozen. There we go. Okay, right, so here, right, Fourier transform, plug in a function of f, we're going to end up with the function of omega. Turns out we can undo this process, right? We have a method for plugging in a function of omega and then integrating out omega in a certain way and ending up with a function of just x. Okay? And so that's this inverse Fourier transform. Okay. And so here, what we're going to say is, well, so here we're assuming that f is a function of omega. Okay. And what we're going to do is we're going to define the inverse Fourier transform as kind of this calligraphic f inverse applied to our function of omega, capital F. If we want to go from omega to x, right, we want this whole thing to be kind of a function of x in the end. And so that's this argument x. But what is this operation, right, kind of f to the -1 of f? Well, what we do is we just integrate out our function of omega multiplied by e to the I omega x, right? And so two things to keep in mind. One, the sign is different than kind of the forward Fourier transform. The other thing is, right, we don't have a constant in front. Okay? But otherwise, right, we're integrating out omega. The only free variable in this integral now is an x. So this whole thing is now a function of x. Okay? Right, and so the thing to notice is that, well, if you take the Fourier transform of a function, right, which we just defined back here, so plug in a function f, get out this thing right here, and then take the inverse Fourier transform, what we're going to end up with is the original function f, at least where it's continuous. Okay, and we can see this just by, right, explicitly computing this, right? So here we're saying, what is the inverse Fourier transform of the Fourier transform of a function f evaluated at point x? Okay, well, let's start with the inverse Fourier transform, right? Coming from this formula, what we're doing is we're plugging in here. That's the Fourier transform of f, or f hat, you might write. Okay, and so what is that Fourier transform? Well, there's a coefficient here missing. There should be a 1 over 2 pi in front. But if you plug in kind of the definition of this object, right, that's exactly 1 over 2 pi times this integral. Okay, and then again, multiply by e to the I omega x. But this was the representation that we started with for f, right? And so this whole thing right here is exactly just equal to f of x. So if we take the inverse Fourier transform of the Fourier transform of our function f, we end up with f again. Okay. So this inverse Fourier transform really is an inverse operation to the Fourier transform. Cool. Okay, so as I mentioned kind of at the start, one of the important pieces that we'll be working with are these Gaussians, right? Which are e to the, say, minus alpha x squared, or e to the minus beta omega squared, whatever you want to plug in, but you have an argument that's squared, and then like a minus coefficient times that, and then take the exponential of that. Okay, so functions of that form are called Gaussians, turns out that kind of working with Gaussians, those are actually kind of the right sort of basis functions to work with in the context of infinite intervals. And so those will give us nice representations for a lot of solutions that we'd like to compute, especially if we don't want to have to deal with kind of dealing with these Fourier transforms and dealing with integral identities that look like this. We'd like simpler ways of expressing things like this, and it turns out that these Gaussians are the right way to do that, or a good way to do that. Okay, so what we're going to start with are kind of Gaussians of this form, right? So these are going to be functions of frequency. They're going to exist in frequency space, and we're going to define them via g of omega, right? So our Gaussian is capital G. What is this function? It's e to the minus beta omega squared. And so the question is, well, why are these called Gaussians? So these in practice are the probability density functions for a Gaussian distribution. Or you might have also heard them as bell curves or normal distributions. Okay, but these kind of play an important role in these Gaussian or normal distributions. And so then the question is, well, right, what's the role of this parameter beta? So what we can do is we can sketch a few of these. So when beta is relatively large, or sorry, I should say relatively small, we're just going to get some kind of profile like this, right? So of course, when omega is equal to 0, the value of our function is 1. And this is 0. This is positive for every possible real valued beta and omega. Okay. As omega tends to infinity or negative infinity, this whole thing tends to 0. And so then that's how we get this distribution or the shape, etc. Okay. So this is a normal distribution for one value of beta. But what we can do is kind of plot another value. Okay. And so it turns out that if you increase beta, right, kind of the profile of your function is going to look something like this. And so this would be beta equals 10, right? Right, as you increase beta, the profile of the function is going to be more peaked. As you decrease beta and as beta goes to 0, right? Well, if you plug in beta equals 0, you have something that's effectively just 1 for every possible omega, right? So as beta gets smaller and smaller, you'd expect the profile of your bell curve for this Gaussian to be kind of wider and wider. But anyways, okay, so these are kind of the basic building blocks that we'll be working with. And so the first question we're going to ask is, well, what is the inverse Fourier transform, right? So here we're defining these in terms of frequency. These are functions of frequency. If we'd like to convert them back to kind of functions of space or right, functions of x, then we need to apply the inverse Fourier transform by integrating out omega. Okay. And so that's what we're going to do. So we're going to call kind of the inverse Fourier transform of G, capital G. That's going to be lowercase g. And so by definition, what is this function? Well, just integrate out g omega times e to the I omega x, and then integrate out kind of that omega piece. Okay, in this case, we know what g of omega is. So we can plug in, right, g of omega here, and this is the this is a piece that we end up with. Okay. So now the question is, well, can we evaluate this integral? So the answer is yes, and there are a number of ways to do this. Okay, and so this is one solution. What is g of x? It's going to be some constant, right? Square root of pi over beta times e to the minus, and I can write this bigger. So g of x, this becomes square root of pi over beta times e to the minus x squared over 4 beta. Okay, which we can also write as square root of pi over beta e to the minus 1 over 4 beta x squared. And so the observation is, well, right, the inverse Fourier transform of the Gaussian, this little g of x, is also a Gaussian, right? Because sure, we have some constant in front, and then we have an exponential of minus some constant here times the argument squared, which already is interesting, right? So if you apply this Fourier transform to this family of functions that are Gaussians, right, you're going to end up with another Gaussian. And so maybe calling these Gaussians like eigenvectors or eigenfunctions of the Fourier transform, it's not totally valid because, in part because you're changing the argument a little bit. But what is more mathematically sound is to say that the Fourier transform, or say Gaussians are invariant with respect to the Fourier transform, right? Plug in a Gaussian, you're going to get a Gaussian back. So you're staying within the same class of functions. Okay, and so as I said, we're not going to kind of explicitly compute this integral or kind of go through the steps. I mean, there are a number of ways of doing that, especially if you've had some complex analysis. One kind of nice way to do this, though, is, so I'll write it here. So what you can show is that, maybe I should write it here. What you can show is that this function g of x satisfies this differential equation. G prime of x is minus x over 2 beta g of x, with the initial condition g of 0, which if we look at the integral, right, g of x is this integral, plug in x equals 0, you're going to plug in a 0 there. So this whole thing is 1. So we just have that term. So g of 0 is going to be the integral from minus infinity up to infinity of e to the minus beta omega squared d omega, which you can do a change of variables to get 1 over square root beta integral from minus infinity up to infinity of e to the minus z squared dz. And this integral, right, negative infinity to infinity of e to the minus z squared dz. Let me write it here. So this integral here, this turns out to be the square root of pi. And so this is something that's often taught in like a multivariable calc course, where you say what this integral, this is equal to some quantity I, and so you square it, you're going to get I squared as some integral. Change the polar coordinates, you can actually evaluate it, you're going to get I squared is equal to pi, and so then take the square root. Cool, but okay, great. Anyways, yeah, so what you can do is you could say, well, whatever kind of this inverse Fourier transform G is, it satisfies this differential equation with this initial condition. G of 0 is square root of pi over beta. And you can solve that ODE and get this exact same thing. Okay. So one question is, well, where do you get this differential equation from? If you go back here, right, take the derivative of this, you're going to end up with G prime of X. This is going to be what? Integral from minus infinity up to infinity, e to the minus beta omega squared times I omega e to the I omega x d omega, right? Because the only thing here that depends on x is this term. Differentiate by x, this I omega is going to come down. And so then what we do is we integrate by parts, where kind of this is the derivative that you're integrating. One of the appendices in the book has more details on this approach. Okay. Cool. So great. So we know what the inverse Fourier transform of a Gaussian is. It's another Gaussian. And turns out we can use this to figure out kind of what the forward Fourier transform of a Gaussian is. Right. So if we plug in this function e to the minus alpha x squared, we want to take the Fourier transform of that. Well, what do we get? So, right, let's take the Fourier transform of this thing right here, and then relate this function back to that. Right. So if you plug in G, right, G was the inverse Fourier transform of capital G. So the Fourier transform of G, that's going to be Fourier transform of the inverse Fourier transform of our function G. These cancel each other out, so we're just left with G of omega. So Fourier transform of this function, right, little g of x, which we computed up here, that's going to be capital G of omega, which we define to be this thing right here. Okay. How do we compute this Fourier transform? Well, that's just an integral. So we have a constant in here. Constant can come out of the integral. So we're left with this expression, right? So this constant times Fourier transform of this function here is that. Move this constant to the other side, we end up with this. Okay. And so what we really want to do, right, we're almost there. It's just we have this, right, minus 1 over 4 beta, where instead we want the coefficient to be alpha or minus alpha. Right, so what we're going to do is we're just going to set alpha to be 1 over 4 beta, so that if you plug in, right, take this 1 over 4 beta, plug it in for alpha, we're going to get the Fourier transform of e to the minus alpha x squared. Plug in for beta here, you're going to pick up a 1 over 4 alpha pi, and the square root of that, times e to the minus omega squared over 4 alpha. So in this way, we've computed both the forward and kind of backward or inverse Fourier transform, at least for Gaussians. Okay. And so we're not really going to do anything with this fact in this chapter, but in the next chapter, they'll come back in a kind of fundamental role. Okay. So, right, as I said, right, calling Gaussians eigenvectors or eigenfunctions isn't necessarily the right vocabulary because, right, you're changing the argument. It's not really an eigenfunction, but they are invariant with respect to the Fourier transform, right? Take a Gaussian, take the Fourier transform, you're going to end up with a Gaussian. So you're in the same family of functions. And so kind of one question we can look at is, well, what happens, right? What is this Fourier transform doing to Gaussians, right? So what we can do is we can say, well, right, take one of these Gaussians, okay, and suppose alpha is small, right? So I'll copy the picture that we drew before. Something like that, right? So again, so if alpha is small, just show it. Okay, whatever. If alpha is small, then the kind of the profile of the Gaussian is going to be more spread out, right? And so then if we take its Fourier transform, right, what's going to happen is, right, the Fourier transform of e to the minus alpha x squared, that's going to be 1 over, or the square root of 1 over 4 alpha pi. Okay? So in this case, with alpha small, the 1 over 4 alpha pi, that's going to be large. Otherwise, we have the e to the minus omega squared over 4 alpha. Okay, so with alpha small, that 1 over 4 alpha is going to be large. Okay, so if we have a Gaussian, right, with a small kind of parameter, and we take the Fourier transform, in the frequency side, that corresponding Gaussian, right, the parameters are going to be large, and so in a sense, kind of the distribution of that Gaussian is going to be peaked near omega equals 0. And so it's not just, right, so in this case, right, we also have this term that's going to, what's going to happen is when omega is equal to 0, this term right here is going to make kind of the value not equal to 1, and likely larger than 1. But the point is that, right, when we take the Fourier transform of Gaussian, if it's spread out, the Gaussian is spread out, then the Fourier transform is going to be localized to 0. And you can do the same analysis reverse, right? If the Gaussian is localized, right, and it peaks near 0, you take the Fourier transform, then the resulting Gaussian is going to be spread out. Okay, so there's a sort of interesting, you might say, like duality going on with this Fourier transform, right? It sends Gaussians that are spread out in space to Gaussians that are localized in a frequency. And likewise, if a Gaussian is localized in space, then the Fourier transform is going to send it to a Gaussian that's spread out in frequency. Okay. Yeah. And so in the next section, we're going to use these Gaussians to explicitly construct solutions to kind of the heat equation, especially solutions that are a little more nicely computable than, say, representations like this.